All right, so the first one, 0.60 atmospheres over 1. So how would you convert that to millimeters of mercury and torque? Multiplied by 760. Good. So you end up with $456. But how many sig figs do we need? 2. Very good. 460 millimeters of mercury. And that's going to be the same in torque. Because 1 millimeter of mercury is equal to torque. The second example, I always joke about this. Now, if your blood pressure is too high and you need to get put on a medication, you can just convert your blood pressure to atmospheres and then suddenly it's lower. Right?
So
I don't have high blood pressure. What are you talking about? Especially right before a chemistry exam. All right, so 1 torr is how many atmospheres? I'm flipping it around. 60. Yeah, so I did this on purpose. It is very easy to mix up what goes with 1 and what goes with 760. So remember that 1 and ATM always go together, and then 760 goes with your millimeters of mercury or torr. So 760 torr. So you divide that out. So 115 divided by 760. So how many sig figs? 1, 5, 1, ATM. And we'll do the same thing here. And how many sig figs do I use for this? 2. So it's going to be 0.099. Good. And I think I told you this story about a medicinal chemist who was told his blood pressure was too high. He needed to go on a blood pressure lowering medicine. Either lose 15 pounds or take this medicine. And he lost 15 pounds so quickly. Because he didn't want the side effects of the medicine. So.
My grandpa is completely done with blood pressure medicine.
Mm-hmm.
And when my grandmother bought a treadmill and they're 75 years old, they've gotten off most of their meds. My grandmother's got them on cholesterol meds. They just pretty much run and walk at 75 on a treadmill every day.
That's good. Good for them. That's too.
It actually went to the doctor the other day. It was like 960 over 130 or something. It was just, I'm like, you're gonna have a stroke. He has blood pressure medicine.
Sometimes you get a really bad reading though, because people get really nervous when that
Yeah.
cuff tightens up. Like a lot of people get like anxiety when they start to check your blood pressure.
I know, yeah. I think it's hard, and so much of it depends. It seems like in the U.S. they've been lowering the blood pressure to, like, it's not clear whether it's the pharmaceutical companies who are kind of like saying, this is high blood pressure, keep lowering it. So.
I had a class before where our professor said it was like they came up with blood pressure by like the averages for blood pressure by like Harvard male students or grad students or something did a study, and that's how they came out with those like the average blood pressure readings. And I guess that, you know, they're so outdated that, you know, we still go by that.
Yeah. Seems like a lot of things are like that.
Be in the way.
Yeah. Okay. On the next few things that we're going to talk about the relationships between the different descriptions that gases can be classified by, the pressure and volume, temperature, molar amount. In your textbook, now keep in mind your textbook is for a 2-semester chemistry course, so there is no way we can cover all the information in your textbook in one semester. We do a great deal already. So if you happen to read the textbook and say, you know, I want to review this section, omit all the math. There's no math in this section. And then do not memorize the names of the scientists. You know, some of it's Boyle's Law, Dalton's Law, all that. Do not take up precious space for that. We're just going to talk about the relationships. And it's not as complicated, you know, as I'm making it sound. But if you turn to your textbook and you say, oh, I'm just going to review these gas laws, and you're like, oh my gosh, so my blood pressure is going up now. So pressure is inversely proportional to volume. And this is when everything else is held constant. So when I say everything else is held constant, I mean molar amount and temperature. So the way these gas laws work, it's usually two relationships that you're talking about varying, and then the others are held constant. So if you increase the pressure, you decrease the volume. Or vice versa. If you decrease the pressure, what's going to happen to the volume? Increase the volume. So what happens when your child lets go of this helium balloon and it floats into the sky? What eventually happens? They scream, yes. Or my sister, when she was little, she kind of has this, she lives in a fantasy world, and she still does to this day, but she's like, oh, Dad can just climb up a ladder and get the balloon, you know? And then, meanwhile, I'm like, there's no way he's going to get that.
It loses its.
Right. So what happens as a balloon goes up? The atmospheric pressure goes down. So your pressure goes down, and then what happens to the volume of this balloon? It's going to increase to the point where it's explode. Yeah, explodes. So hopefully your child doesn't see that. See? Okay.
Luckily, it usually goes up high enough.
Yeah.
Usually disappears into the clouds,
Yeah.
or they get back in the car.
Or you get, yeah, or, oh, we can get another one. So, okay, so that's the first relationship. Again, don't worry about math or the names of the scientists. Now, volume and temperature. When everything else is held constant, and everything else that is held constant would be molar amount and pressure. Not that you need to be concerned about this. All I want you to focus in on is the relationships between these two variables. So volume and temperature are directly proportional. So if you increase the volume, you increase the temperature. If you decrease the volume, what happens to the temperature? Decrease the temperature. So hot air balloons, I don't know if any of you have the chance to go to that hot air balloon festival. I know it's cool. So the air in hot air balloons is heated, and what happens to the volume? It increases. So, and the volume increases. Pressure and temperature. Pressure and temperature are directly proportional. So you increase the pressure, you increase the temperature. And a lot of times students say, well, what about that one we just learned before? Remember that you're changing two variables and holding the other two constant. So we're just looking at the two that are changing. So if you increase the pressure, you increase the temperature. If you decrease the pressure, what happens to the temperature? Decrease the temperature. So if you heat a sealed can of soda, the pressure of carbon dioxide in that can is going to increase. I had a student when we were learning this. She was like, "Oh, that explains why." When I went out to my car and I wanted this soda, and it was in the summertime, I wanted this soda, and I opened it, and it just went all over her car because the pressure, the temperature had increased, and the pressure had increased.
So your volume and your molar are going to stay the same?
Right, volume and molar amount are the same. And that's, we're talking about the gas. So this is not having anything to do with the liquid, but the gas that's in the tank.
How much is it when you put like in the freezer? And then it like pops up.
Well, that has to do with water. The water in the soda. Because water is unique. When you freeze it, it expands. So it doesn't have anything to do with the gas. The gas, when you decrease the temperature, the gas pressure decreases. But then you're dealing with a whole different thing with water. When you freeze water, it expands.
So it has nothing to do with the gas and it's with water.
Yes.
You ever seen like when they take a water bottle and they set it on its side and freeze it, and then if you pick it up slowly, the cap open warm, and it instantly freezes it?
Is this?
They do it with a beer bottle, not a lot. They super cool it, but it's still
Yeah.
liquid, and then they agitate it, and it just cascade freezes.
Very cool. Yeah, so they're doing the super cooling. So they're going from.
But they do it in a regular freezer. They just leave it alone, and it drops below its freezing point. It stays a liquid.
But it has to be sideways.
Oh no, that one's sitting up.
Oh, okay.
Oh, well,
And what happens when it goes sideways?
that's how it was showed it. Like,
But it shatters.
no, when you hit it, it like instantly, you can just see it.
Oh, it crystallizes.
Yeah.
I got you.
You said like
Yeah, that is cool. I've seen it before, so now I know it. All right, volume and molar amount. Volume is directly proportional to amount. So remember, the amount is the number of moles. So you increase the volume, you increase the number of moles. You decrease the volume, you decrease the number of moles. So if you think about blowing up a balloon, as you blow up a balloon, the amount of molecules inside the balloon increase. And the pressure and temperature are held constant. So the take-home message from all of these gas laws is really the relationship between these four things. The only relationship that is inverse is pressure and volume. So I have a lot of students that when they get their exam, they just write down this right away and the arrows. So if you increase the pressure, you decrease the volume. Everything else is a direct relationship.
And did you already say at the top that the state
Oh.
is constant pressure?
So then, like, on the test, it'll give us a scenario like the example, and
Yes.
we'll have to not write the property, write what it does, or
Possibly you could just be asked a true-false question. You know, like how if you increase the pressure, what happens to volume? Like,
okay.
as pressure is increased, volume increases. True or false? Something like that. Okay. So the next thing we're going to talk about liquids. So you have this bottle of water and it's sealed, and when you squeeze it, you feel that there's resistance because there's pressure. Why is there pressure on the sides of this bottle?
Is the water
The vapor, yeah. So remember, you have your liquid water. That is in equilibrium. These arrows mean equilibrium arrows. You have your liquid vapor, or your liquid water, that is in equilibrium with the gaseous water, or water vapor. So there are gas particles in this water bottle. Now, if you think about what happens if you left the bottle uncapped for several days, what happens to the level of the water? It decreases. So that's because your liquid's going to a gas, the gas evaporates, and it leaves the bottle. So when you squeeze this bottle and you feel pressure, you're feeling this gas pressure. So this is called vapor pressure. So this is the pressure gas exerts above a liquid. So changes in atmospheric pressure will cause a change in boiling point. Now remember your boiling point. This state change that you're going from liquid to gas. So if you've ever tried, maybe you went to Colorado skiing and you tried to save money by cooking your meals. And what do you notice about cooking in Colorado? It takes a lot longer. Surprising. Oh, this spaghetti should be done, but it's not. So if you look at instructions, like, cooking instructions on brownie boxes and cake boxes, it says for higher altitudes, cook this long or at this temperature. So that's because the changes in atmospheric pressure will cause a change in boiling point. So at high altitudes, atmospheric pressure is lower, so the pressure decreases. So the boiling temperature will be what? It's going to decrease. So we're decreasing the pressure, and what happens to the temperature? You decrease the temperature. So the boiling temperature will drop. So this means when you boil your spaghetti, you're trying to cook your spaghetti here, the boiling point is roughly 100 degrees Celsius. But when you go up to higher altitudes, it's not going to be 100 degrees Celsius. It might be 95 degrees Celsious. So it's going to take longer to cook. So at low altitudes, atmospheric pressure is higher. Pressure increases. So the boiling point will increase. All right, so last page of our note packet. Just in time, huh?
Do you need to know what partial pressure is?
Partial pressure, yeah, it's the contribution of a gas to the total pressure. And on the next page, we'll talk more about partial pressure too. So on page 45, the last page of our note packet, we are going to use partial pressures to calculate the total pressure of a mixture of gases. So the total pressure is the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, and so on and so forth. So depending on how complex of a mixture of gases you have, it could be just 5 partial pressures, or it could be 2 partial pressures. In a mixture of gases, each gas contributes to the pressure independently of the other gases. So these calculations, they seem really intimidating, and I have a lot of students who blow these off and say, oh, I don't have time to study this. Study this, because these are the easy points I'm going to have. These are easier than the conversions that we've been going over. So a mixture of gases contains nitrogen and oxygen. The partial pressure of nitrogen is 0.8 atmospheres, and the partial pressure of oxygen is 0.1 atmospheres. What is the total pressure of the mixture? So P total, we're just going to take the partial pressure of nitrogen. And is nitrogen a Hofbrinkel? Yeah. And then what about oxygen? It's a Hofbrinkel too. Good. So I'm going to take 0.8 atmospheres and 0.1 atmospheres and add that together. And that's how you get the total pressure. That's it. So 0.8 atmospheres plus 0.1 atmospheres gives you 0.9 atmospheres. These calculations will force you to think about your sig figs, because remember, this is addition. And addition and subtraction have slightly different rules than multiplication and division. Remember, it's after the decimal. So this has 1 after the decimal here. This has 1 after the decimal. So my answer cannot have more than 1 after the decimal. Good. So the last question I want you to work on, the mixture of gases contains helium and hydrogen. The total pressure is 780 torr. The pressure of hydrogen is 600 torr. What is the partial pressure of helium? All right, so how do you set this one up? Good. And you're solving for PHE, so PHE is going to be P total minus PH2. Good. So you have 780 torr minus 600 torr. And you end up with 180 torr. Did I use the correct number of sig figs? Yes. No, you don't have to do all those steps. Yeah, definitely. Whatever works for you. The other thing is, I didn't ask you to convert it to atmospheres or anything. So if I didn't specify, you can leave it in the units that I give it. There might be a time where I give you the partial pressure. Maybe I'll give you the partial pressure in atmosphere, total pressure in torr, and then you might have to convert one to the other. Don't do that.
We're good.
Yeah, we're good. Okay. Questions about that? All right, so we're done with Unit 2.